Hi, Kat. What are you doing?
Oh, hey, John. Oh, not much. I'm just making some quantum dots today.
Ooh, that sounds cool. What are those?
I'm glad you asked. Quantum dots are very small, nano-sized crystal particles made of semiconductors that, when exposed to an excitation source such as UV light or electricity, emit photons of colors in the visible range. The variation in color is due to the different sizes of the particles. So the smaller the particle, the bluer the emission, and the larger the particle, the more red the emission. These properties are attributed to quantum mechanics. Now there's a few key concepts you need to know to understand how they work before we get to the quantum parts, so let's dive right in. First, let's look at the scale of these particles. They're absolutely tiny, considering the smallest size the human eye can see is about 10 micrometers, so the best case scenario is seeing something the size of these red blood cells here. But quantum dots range from about 1 to 10 nanometers, which means you would need a really good specialized microscope to be able to see them individually. As mentioned before, the quantum dots are made of semiconducting materials, and a semiconductor is a material that can exhibit properties of a conductor and an insulator, and is commonly employed as a charge carrier. Some common semiconducting materials that compose quantum dots include cadmium selenide, cadmium sulfide, indium arsenide, or even carbon. These materials can all be tuned in a synthesis to grow to various sizes that will emit different colors. Common semiconducting materials include silicon that make up a lot of the chips and transistors that are in our phones and our computers. Basically, anything that's computerized or uses radio waves depends on semiconductors. When a quantum dot is exposed to an excitation source, such as a UV lamp, it absorbs a photon. With this photon, electrons are provided with enough energy that allows them to break free from the valence band and jump up to an empty energy orbital. Then the electrons relax back to the valence band. During this relaxation, a photon is emitted. The color of the emitted photon is dependent on the energy gap between the valence band and the empty orbital. Quantum mechanics dictate the behavior of very small particles. At this scale, within molecules, quantum confinement states that the smaller the particle, the larger the gap between the conduction and valence bands, and the higher the energy of the photon emitted. With this material, cadmium telluride, if you were to shine a UV lamp onto a macro-scale piece of cadmium telluride, you would notice that there is no emission of photons that are visible to the human eye because the band gap at this size is very, very small. According to the Planck equation, E equals h nu, or E equals hc over lambda, the higher the energy of a photon, the lower the wavelength of the photon, and as you can see here with the visible spectrum, energy increases as you sweep from red to blue, so higher energy photons are blue or purple. And these high energy photons come from smaller quantum dots. So, you may find yourself asking, why are quantum dots important? Well, they're found in a lot of things in our everyday life. For an example, quantum dots are being employed as LEDs for use in TV. Their benefits in this field include that at this time, the quantum dots are a much cheaper inorganic alternative to the OLED or organic light-emitting diodes that make up TV screens today, and they are also much more energy efficient. These quantum dots are also being introduced as a material for photovoltaic cells to harness energy from the sun. Last, but certainly not least, quantum dots are able to be used as fluorescent labels for biomedical imaging. A lot of work and research remains to be done surrounding these particles, such as developing less toxic, high-quality quantum dots, but for now, there's been a giant door opened into the future of these particles being used in technology and medicine, and they're absolutely beautiful, so what more can we ask for?